Hey, chapter 20 on air pollution for AP Environmental Science. That's a little quote to start the day by Michael J. Cohen. I thought I saw a blue jay this morning, but the smog was so bad that the poor bird turned out to be a cardinal holding its breath. Reality is 1 in 6 people breathe unhealthy air. Remember during the Beijing Olympics, a lot of marathon runners actually didn't go because the air was so bad. And of course, they tried to remedy that by not driving cars, rather, for a couple months ahead of time. But yeah, it's still bad. And that's an example of what's called photochemical smog or industrial. A natural indicator of just how polluted an area is lichen moss, which can grow on rocks, it can grow on trees, it can really grow anywhere. It lives in all regions, even the Arctic region. It's something that caribou up there / reindeer eat. Anyway, if there's no lichen in an area, that's bad. That means that it's very heavily polluted. My guess is over in the Beijing area, it is very lichen-free. If it is gray-green, that means there's some pollution out there. If it's orange and leafy, kind of like the picture there, that means it's not a very polluted area. So around this area, an urban kind of area where we are, our lichen moss, if you go outside, is very gray, very greenish in color, meaning relatively healthy, but we have some pollutants into the air. So this is a natural indicator. If you go outside of this area, of course, to like northern Wisconsin, it's going to be much cleaner air. The atmosphere, obviously, we can't talk pollution without talking atmosphere. It's a thin layer of gases, differing temperatures. The higher you go up, of course, the colder it is. When you're flying at 38,000 feet in an airplane, it's about minus 40 degrees Fahrenheit. We have increased pressure closer to sea level, so we have greater pressure here because of the gravitational pull of molecules than we do in Denver, for example. Different composition we'll take a look at. Atmospheric pressure, of course, is mass per unit area of air. Sea level has the highest density, and it does decrease with altitude because gravitational decrease. Here are the different layers that you are going to need to know. The first one, the one that you are sitting in right now, is called the troposphere. That has the greatest density of particles, so therefore has the greatest pressure. Then and that's where our weather occurs. That's when you fly a kite, that's where it is. Airplanes tend to fly kind of on top of that layer. The stratosphere, very important because that is where this magical thing called O3 is. O3 is our ozone layer, and that protects us from UV rays. Then above there, we've got the mesosphere, and then we've got the thermosphere. Above there, mesosphere is known for the layer that's very thin, but it actually protects us from meteorites. Actually, they're called asteroids when they're outside of our atmosphere, and once they enter our atmosphere, they are called meteorites, and you can see those burning up, and of course, those are shooting stars. Thermosphere is the region way up there where like our satellites are going. So the troposphere, 80% of our air mass, responsible for weather patterns, extends about 11 miles up at the equator, and it does narrow as it gets toward the poles. That's why when you fly to London, you go up near the Arctic region because the atmosphere is thinner, you get less air resistance, and therefore the plane can go faster and use less gas. Troposphere is 78% nitrogen, oxygen. So here it is, another example. We get the troposphere here, we get the stratosphere here. Unfortunately, now, stratosphere has the ozone layer, the O3, which protects us from UV rays. Unfortunately, a pollutant that we get is what's called photochemical ozone. So sometimes that ozone actually appears near the ground level we are. That's a pollutant. That is actually a respiratory irritant for us. And we have ozone action days to protect against that. So let's get into that in a little bit more detail. So the stratosphere, about 11 to 30 miles up, a very high concentration of ozone. Oxygen molecules interact with UV radiation. So here's the chemistry behind it. What happens is we have oxygen molecules that react with UV rays, and we get, in this case, resulting 2 ozone molecules way up there. They protect us from harmful UV radiation. It actually, if we didn't have that ozone layer, we'd literally burn up because of the UV. It actually protects us from sunburn, cataracts, cancer of the eye and skin, damage to the immune system. Evidence of decrease in good ozone in the stratosphere, that's a bad thing. And we have an increase in bad in the troposphere. So what's really happening is way up in the sky, we're losing our ozone layer. And what's happening is the UV rays are then allowed to penetrate further down on the Earth, and what happens is those UV rays plus the oxygen that we have down here is creating ozone right near our We have outdoor air pollution. Outdoor, in other words, for outdoors, ambient. We get natural sources. The reality is we're going to get natural things that produce pollutants, everything from volcanoes to dust. If you go to Arizona or Nevada, they get dust storms, things like that. Those are deemed pollutants. We also have volatile organic chemicals. Those are VOCs. Isoprene, which is given off by a plant, is actually deemed a VOC, and that can contribute to photochemical smog. Forest fires, of course, burning of leaves, volcanoes, sea spray, actually all deemed air pollutants. The problem is, or the good thing is, they rarely reach harmful levels because nature takes care of nature. It's a beautiful thing. These things can affect climate naturally, health, particularly in urban areas. The good thing is a lot of things, like in the region we live, wind carries a lot of these pollutants right away. It goes over to the Great Lakes, and a lot of regions don't have that. So, human impact on the atmosphere, really three things to look at: burning fossil fuels, using nitrogen fertilizers and burning those fossil fuels too, refining petroleum and burning fossil fuels and manufacturing, bad things too. So let's dive right into this. First of all, burning fossil fuels, what it does is it adds CO2 and it adds ozone into the troposphere. This can lead to, of course, the big chemical CO2 that can lead to global warming. It can alter climates. It can produce acid rain. We'll break this stuff down a little bit later too. What happens with nitrogen? We use a phenomenal amount of nitrogen on our farm fields. You might even use it on your lawns. What happens is that releases nitrogen oxide, NO2, N2O, and NH3, which is ammonia, into the troposphere. That can actually get up into the atmosphere and produce what's called NO3, which is nitric acid, and of course that can produce acid rain. Looking at industry, of course, we burn a lot of coal. A lot of that coal actually releases SO2, which is sulfur dioxide, into the troposphere. In the great state of Wisconsin here, we have a lot of paper mills. SO2 is actually released as a natural byproduct of that process, and of course that can lead to acid rain. Eventually that can form with water and cause what's called H2SO4, which is sulfuric acid, and that's acid rain. It can release also, when we burn fossil fuels, heavy metals into the atmosphere like lead, cadmium, and arsenic into the troposphere, and obviously that's. Cities usually have a very high pollution rate, more than rural areas. Obviously more people here, more industry here, plus the big buildings tend to block the winds that oftentimes carry the pollutants away. Most people exposed to extreme pollution are in developing very clean air in the United States. A couple ways of looking at these pollutants: there's primary and secondary. There's also mobile and stationary. Mobile is, hey, you're in your vehicle, you're moving. That's a moving source of pollution. Stationary is like a factory that's going nowhere. So, breaking this down, we have primary pollutants. Those are very simplistically individually put into the atmosphere, and then what happens is these primary pollutants have a party, get together, and form what's called secondary pollutants. So a bunch of them come together among some other things, including like water, more oxygen, and create these secondary pollutants, which are terrible. So major classes of air pollutants: carbon oxides. We generally write those, by the way, anything with carbon in it like this, we put a little COX, and it covers a lot of things like carbon oxides, the CO and the CO2. Sulfur oxides, SO2, SO3, we'll break this stuff down. Oops, we usually write that as SOX. Nitrogen oxides, like nitrogen oxide here, NO2, which is nitrogen dioxide. Nitrous oxide, you might have heard, that's used at the dentist's office. NO2 are often clumped together to form, as I said, NOXs. We just write it that way. Volatile organic compounds are things like methane. Cows give that off. Propane, chlorofluorocarbons, which are CFCs. Even gasoline, when you pump that gasoline into your car and you like that magical smell, well, what happens is that's a VOC that gets in the atmosphere and leads to something called photochemical smog. Suspended particulate, think of that dust, soot. Think about people in the city burning leaves. That puts that little soot in the atmosphere when you have a fire in your fireplace or a fire pit in the backyard or whatever the case may be. We also have things like liquid droplets like sulfuric acid, PCBs, dioxins, pesticides included in here. Photochemical oxidants are ozone, something called peroxycyl nitrates, which is PANs. We'll call them in H2O2. We have something called aldehydes too. I'll break this down a little bit more. We also get some radioactive substances, radon-222. That is something that may be naturally occurring in your basement. Hazardous air pollutants, also known as HAPs, those are nasty, tend to be chlorine-based, things like carbon tetrachloride, methyl chloride, chloroform benzene, ethylene dibromide, and formaldehyde. The one we're going to probably focus on in that one is formaldehyde, which might be for dead bodies. Anyway, outdoor air pollutants, primary, enter directly into the atmosphere. That includes soot, CO, which is carbon monoxide, carbon dioxide, and nitric oxides. Secondary is when those primary pollutants have a party, they interact with each other and make things worse. That is a synergy. 6 main outdoor pollutants. These are the ones that are targeted as the ambient nasty ones. Carbon monoxide comes out of your car. Nitrogen dioxide comes out of your car, and it also comes from fertilizers. Sulfur dioxide, you're generally associated with burning coal from industry. Suspended particulate matters, smoke, soot. Ozone and lead are deemed 6 main outdoor pollutants that we need to avoid. And of course, you know lead is bad. So here they are. Carbon monoxide, you can read through these in your book a little bit more too. Everything from cigarettes, they come from there, and complete burning of fossil fuels. Hopefully you have a CO monitor in your house. And it does come from motor vehicle. It does react with our hemoglobin, of course, blocks it. And if you have a malfunctioning furnace, for example, from it. Nitrogen dioxide, reddish-brown irritating gas, gives a photochemical smog its lovely brownish color. It can be converted into nitric acid, as I said before, HNO3, major component of acid deposition. Fossil fuel burning in motor vehicles is the major source, along with power and industry plants burning the stuff too. It's a lung irritant. It aggravates our asthma, chronic bronchitis, so it's sulfur dioxide, SO2, what happens is we have sulfur-containing fossil fuels such as coal and oil. So what happens when we burn that coal, remember there's 3 levels of coal. Anthracite is by far the least sulfur content. Bituminous has a very high sulfur content. What happens, we burn that sulfur, it gets in the atmosphere, forms with oxygen, diatomic oxygen, and we get magical SO2 in the atmosphere. Eventually that can be converted into sulfur trioxide and eventually into sulfuric acid in a natural process. That's a secondary pollutant, and that is going to cause acid deposition. Suspended particulate matter, as I said, things like aerosols are included in here. It could even be things like smoke, dust, haze. So where did a lot of the suspended particulate matter, also known as SPM, come from? Well, burning coal, power plants, industrial plants. Nowadays we have these things called scrubbers, which actually takes a lot of this out, so it's getting much better. Vehicles, agriculture, just plowing up a field is going to kick up dust. What does it do? It knows throat irritant, lung damage, bronchitis, aggravates bronchitis, asthma, shortens life. Just a lovely, lovely thing. Anyway, ozone, description, very highly irritating gas, unpleasant odor. It is forming in the troposphere now. We like it in the stratosphere because it blocks the UV radiation from coming in, but we don't want it down here. It's a chemical reaction with volatile organic compounds, VOCs, emitted by cars and industry with nitrogen oxides. They form photochemical smog, of course, and that is a huge lung irritant. It causes breathing problems, coughing, eyes, nose, throat irritation, and so on. Lead, of course, solid toxic metal, emitted into the atmosphere as particulate matter. It's in paint in old houses. Smelters, which are actually metal refineries, oftentimes give this off. Think about the Great Steel Belt all the way from Pittsburgh all the way through, really, Milwaukee. Lead manufacturers, storage batteries, and leaded gasoline. We used to have leaded gasoline, and now we have unleaded gasoline. So that leaded gasoline, it kept the lead in it, actually was put into the environment. Now, gas was cheaper because we didn't have to refine that stuff out, but it was worse on our environment. Brain, other nervous system. This, of course, carbon dioxide. Should we really consider carbon dioxide a pollutant? There's 3 reasons for classifying it. High concentration of a pollutant can become an irritant. Quite obviously, we need oxygen. If we had only CO2, we would not be around here. It's a toxin to our body. Increase in troposphere due to fossil fuel burning, of course, and clearing trees that absorb CO2. Troposphere is warming, there's no doubt. We'll talk global warming and our global climate change in an upcoming chapter. There's no doubt that CO2 holds temperature longer. The big question with global climate change is it anthropogenic? Photochemical smog, that is a lovely picture of Los Angeles. What happens is auto engines in the coal burning industry plus high temps form what's called nitric oxide. Most common in cities with warm, dry, sunny areas, the reaction to occur. So here's the chemistry behind it. VOCs, which are volatile organic compounds, which is actually given off from cars, which is actually given off from things like gas and putting gas into your car, plus NOx, plus heat, plus UV radiation creates this lovely photochemical oxidants like ozone, nitric acid, aldehydes, and peroxyl nitrates. And that causes that lovely brownish haze over cities. We do have ozone action days. The reason we do that, you don't want to fill up your car, you don't even want to fill up your lawnmower because those VOC vapors go into the atmosphere and they can cause that. So you'll see big signs going downtown that say ozone action days and not to put gas in your car, and that's what that's all about because we don't want to get that smog in this region. And of course, hot smog, here's a little picture of it. Solar radiation, the UV radiations involved, hits the NO2s, again, mainly from cars, but from industry too, and we get these lovely things on the bottom. So we get these lovely things on the bottom like nitric acid, PANs, aldehydes, and ozone. Do plants contribute to smog? Actually, they do. They emit isoprene, which is I believe, an alcohol. It's a VOC, only vital in urban cities. Trees have much more benefits than they do negative. Industrial smog is another type of smog, a little bit easier, hopefully, to understand. Mainly of burning coal and other maybe petroleum products. What happens is, of course, with coal, we release carbon. Carbon combines with the diatomic oxygen. We get CO2 or even carbon monoxide, and we get soot, the particles. S2, this coal, of course, gives off a lot of sulfur, plus oxygen gives us SO2, which is a suffocating gas, and actually can form sulfur trioxide, which leads to sulfuric acid. Sulfuric acid can combine with ammonia in the atmosphere and form ammonium sulfate, and that is the gray air smog. That is nasty. Couple particles, ultrafine particles, and they can actually be lung irritants also. Our sea salt, carbon, of course, tobacco smoke, you know that if you're in a room where somebody's smoking, it is terrible. Combustion nuclei, oil smoke, metallurgical dust and fumes, and even photochemical smog, those are terrible on our lungs. Large particles are things like even pollen, you know that causes you. How do we reduce this outdoor air pollutants? When it rains, it actually clears things out, so that's a beautiful thing. Sea spray along the oceans. Florida doesn't have a lot of pollutants because it's flat, it's windy, and it's got sea spray. Actually takes that stuff out. And of course, wind is going to dissipate it too. Increasing outdoor air pollutants, what happens is urban buildings block the wind, so it stays put and it goes nowhere. Mountain tops, we get this grasshopper effect. Grasshopper effect is, if you think about the old planet Earth, we've got the equatorial regions, got the temperate regions like 45 degrees north, kind of similar to us, and then of course we've got the 0 degree latitude up here, 90 down here, and what happens is we get pollution going from here, and this carries through with the convection. If you remember when we studied weather, we've got heat that rises and then goes and cools. Well, it follows that, and we get pollutants even brought from here up there. So we're finding that pollutants are going from the tropics all the way up into the polar bear region. So it's hitting them, and that's up there too. One last idea is a temperature inversion. What it is think Phoenix as an example of this. Phoenix is the city in the valley, so we get these mountains. We get mountains here. What happens is we get cold weather surrounded by the mountains, and we get an inversion layer. So what happens is we get warm air that traps the cold air down there. The cold air stays, the molecules of the pollutants stay in the cold air, and we get that trapped in there. So what happens is normally we get a nice wind and push all that pollutants out, but because it's in the mountains like that, we get a turbulence that mixes the cold and warm air eventually, and it'll disperse the pollutants, but we get this trapped layer in there because that warm air up there. So these inversions are in sunny climates. We have light winds, mountains on three sides, maybe the ocean on one. This also happens in Los Angeles, because if you know Los Angeles, there's kind of like a picture of it right here. What happens is we've got mountain ranges that prevent it from going out, and those pollutants actually kind of stay in here and create a turbulence, and of course it stays very polluted. All right, that's part one.